All right. Welcome, everyone, to our last talk of GoLab 2020. We have a very special talk for you called Planlagt. I don't know how to pronounce that one, but Distribute Cronwork the Smart Way with Björn Gerdau. And so let's bring him live so you can say hi to him.
Hello, everyone.
Takes just a moment. There we are. Hello. Welcome
Hello.
to GoLab. We are so happy to have you here.
Thanks for having me.
Absolutely, absolutely. It's always fun to see new people coming, and hopefully you'll be part of the GoLab community for a long time to come.
I hope so too.
Fantastic. So all of you who do not know about Björn, he has been working for almost 4 years as a developer at Tarrant Solutions GmbH. He is comfortable with modern development in all his aspects. For sports, he does software architecture consulting and occasionally works on PS2 emulation stuff. We might have to talk later about that. And for our talk today, it is like this. Did you ever dream your background workload would just scale just as easily as your REST endpoints? Enter Planlagt, a distributed work scheduler which automatically distributes reoccurring work, read cron jobs, across all running instances of your service. Configure once and scale at your leisure. Automatic failover and retry logic for peaceful nights. So what does this talk about? Björn will guide you through his headspace of how Planlagt came to be, which problems it solves, and this also includes talking about the backbone synchronized cron task. So I hope everyone enjoys the talk. It'll be in 2 parts with a 5-minute break, and at the end, I hope you will stay tuned for the live Q&A. I want to remind everyone for the Q&A, please direct your questions to the chat bubble with the question mark on it. That's the Q&A one, not the help. So please do that, and we'll talk to you after. Enjoy. Thanks.
Right, so let's get started. Hi, and thank you for joining me today. I'm Björn Gerdau, and today I want to talk with you how a handy little library I developed and still am developing came to be. So who am I exactly? I've been a developer for almost 9 years now, 4 of which at Tarrant. I had some humble beginnings with PHP and friends, after which I ultimately settled on mostly doing Java and Go work nowadays. I also do some consulting work, but my heart goes into designing and talking about cloud architecture. I've developed a few GoLabs myself, some better, some worse. But my greatest achievement, in my opinion, so far are 2 libraries, which saw heavy personal usage in the past. Synchronized cron tasks and Planlagt, both of which I will talk about today in depth. Oh, and of course, we are hiring, so if you like what you see today, maybe give our webpage a look. We are always looking for skilled people. So let's dive right in. If you gave the title of my talk a good look, you might be asking yourself, what the hell is cronwork anyway? It sounds a bit like cron job, but work... let's clear this up, shall we? Cronwork, at least how I put it, is recurring work that you want to scale horizontally. It's more than a simple cron job, as you might know and worked with in the past. You have some recurring tasks and you wanted to scale them with your architecture. it's not enough for that task to be executed in a recurring fashion. You really want that task to fully utilize the computing resources you have at hand. So what are some good examples for cronwork then? Think of anything that has to be done in a recurring fashion and is intrinsically scalable. First example, multi-user data processing. Imagine that we have a platform with a lot of users. Every night we want to do some processing task on each user we have. We could put all that processing into a cron job and have it execute every night. But this is both really ineffective and inefficient. Firstly, we created a hotspot in our architecture which cannot scale with the work at hand. With some clever tooling, like Go, we can parallelize the work, but there's only so much we can do with that one box running the cron job. We can really only scale vertically and give that instance, VM, or whatever it may be, more resources. What we really want to do instead is spread the load as wide as possible and even dynamically add power horizontally, and remember horizontally, not vertically, as needed. A good example for this would be AWS EC2 Spot instances, if you've worked with AWS before. But it's not only about efficiency. With such a big pile of work being worked on by one box, we created a high failure risk. If processing crashes for whatever reason, we lose the whole cron job. If we didn't account for that in our platform with some retry logic, we might have lost the job completely and have to wait for the next execution. That is, in that case, next night. So another example, data polling from an external API. Easy enough, right? This does sound like a prime candidate for a simple cron job, doesn't it? We put that polling into a cron job, have it execute on a fixed schedule, and all's good. That is, unless there's some little detail to consider. Assume that for a whole polling run, we need to call 20 different APIs. Actually, this is the very use case that brought Planlagt to life. Just some foreshadowing. Again, as with the previous example, we can parallelize that with the right tools, but we want to scale this at grand scale. We want to get the most of what we have. Also, the same problems with crashes and retrying from the previous example apply, although to a lesser extent, obviously. So, now that we have defined what cronwork is, let's take a few steps back and focus on the very root of the problem. How do we implement a cron job in a distributed world? To understand how to scale cron jobs, we first need to look at how to implement them in our modern software architectures. So let's stick with the data polling example. We got our sleek, awesome Go service here, which polls data from some external service every, let's say, minute. Assume that we need to make a lot of calls to get all the data we need and that these requests take quite some time. So we really want to parallelize these. So what do we do in the age of unlimited resources? Right, we scale it, of course. Depending on how your deployment of your application looks, that can mean different things. But for now, let's assume we abstractly just deploy more instances of our service. So cool, that was easy, right? Now that we have our service scaled, we encounter a few problems though. First, we need to synchronize them. What does that mean? Assuming our polling is implemented via a cron job and the clocks of the services are reasonably the same, each instance is doing exactly the same thing at the same time. We don't distribute our work, we are just doing it X times over. So the simplest solution to this problem is to implement a locking mechanism. Enter synchronized cron task. Synchronized cron task is a simple framework which basically implements a cron job which is synchronized via a Redis lock. So if we are not familiar with the concept of a synchronization lock, the gist of it is that your running instance sets a value somewhere. In that case, it's a key value pair in Redis. If another instance tries to set the value, it fails, as the value is already set. Only if the service which acquired the lock, by setting that value it is, lifts it again, another instance can successfully get the lock again. So basically, whichever instance executes first gets to pull the data, and the other instances get to do nothing. Still not quite the optimal solution. Still, synchronized cron task lifts a few things off our shoulders. It implements short-lived locks, which are instead actively upheld by the instance to allow quickly recover on failure. For example, a service crash during processing. It implements a bunch of tunable timeouts and spots a graceful shutdown to really make it run smoothly. For bonus points, it optionally implements something called a timekeeper, which allows us to record and export metadata about cron executions. For example, execution duration or failure reasons. Very handy for monitoring and alerting. For more details, refer to the GitHub page linked below. It has quite some documentation. Also, contributions welcome. Side note, synchronized cron task, at least for now, is bound to Redis only, but I'm open to extending it to other log providers in the future. I just happened to need to learn Redis at the time, so I chose that. Anyway, back to our problem at hand. With this solution, our work is synchronized, but still not distributed. So how do we achieve that then? Before we can tackle our distribution problem, we need to again take a few steps back. How does one distribute work in a distributed system anyway? The most obvious answer is put it in a message queue. So what do we have at our disposal? There are many technologies we could use for message queues. Personally, my favorites are Kafka and Redis, although both are not technically message queues themselves, but can be used as such. Of course, this list is not exhaustive. There are many more great message queues, or implementations thereof, out there. As we are already using Redis for our locking mechanism, we'll go with Redis again. But from a technical point of view, any of them would do for the architecture we are about to design. Before we delve into our solution, let's look at some textbook architecture. You most probably have already worked with something like this. We throw in our data onto the message queue, and we have consumers sitting on the other end, transforming or processing it. They might even put it onto another queue for further processing. But thinking back to our problem, could we use this queue pattern much further in the pipeline? How about having the producer produce not data, but tasks, and have them distributed onto consumers? Yeah, this is exactly what we're going to do. Now we are getting somewhere. We are not only able to scale our processing pipeline now, but also the way data is put into our pipeline. Nice. There are already many good libraries to abstract this kind of work, even some cross-language ones. But you might see a problem here. The task producer and his consumers are very tightly coupled. For this system to work, both producers and consumers need to have a strong contract of how tasks should look like and what possible tasks there are. We might put our producer on the same code base as our consumer, but it's still something of a separate entity. What we really want to do is put our producer and consumer right next to each other. Talking about services, we want to have them even in the same service. To really hammer the point home, you might ask yourself why this coupling is such a problem in the first place. After all, you could argue that the same applies to the data pipeline in general. And you might be right. However, the key difference here is a meta one. It's about what a task really is. It's not a simple data bundle which is easy to digest. It is something of an abstract definition of what needs to be done. The producer needs to know this, as he is obviously the one issuing the tasks. And the consumer needs to know it too, as it has to implement the very task. Or to put it differently, there is not a lot of space for interpretation. With data, consumers might decide on their own what to do with it, drop parts they don't need, or alter them as they see fit. But a task is something close to being immutable. So, the solution then seems simple, doesn't it? Put consumer and producer on the same service then. But what does this solve? On one hand, we are not wasting resources. The stability of the task producer now scales linearly with the amount of consumers we have. Or put differently, it scales with the actual amount of pressure in the overall system. And with a locking mechanism, for example with synchronized cron task, we're not wasting any compute cycles either. Also, we address the tight coupling of producer and consumer by having them not only on the same code base, but in the same service. So let's see how this works in the big picture then. We decouple our task production with a Redis lock, distribute the tasks back to our service instances. From there on out, we can scale our pipeline any way we see fit. Bonus points if you scale your pipeline based on system pressure, for example, amount of unprocessed messages on any queue. So, we are going to take a quick break here and give you some time for some Q&A. So we will see us right back.
All right, everyone, we have a 5-minute break. We're going to actually leave Q&A for the end, but it's a great chance to write any notes you may have. So we'll be back here at 24 past the hour. Thanks. Talk to you then. All right, here we are again, ready for the second part of Bjorn's video. So I hope you enjoy and see you at the end for the live Q&A session.
So, welcome right back for the second half of this talk. Phew, that was a lot of architecture talk so far. Now it's finally time to introduce the name father of this talk, Planlagt. Planlagt is, by the way, Norwegian and means planned. I like to give my frameworks funny names sometimes. It can't be helped. So this is it. Planlagt. This ties everything together I have talked in the last few minutes about. So let's look at it step by step, shall we? Planlagt is basically three things. It's a scheduler, a synchronized cron task, and a task manager. We will talk about each part in depth now. At the heart of it all, we have the scheduler. The scheduler is the mastermind behind Planlagt, who pulls all the strings and keeps all the data in check. A scheduler can have multiple schedules. A schedule is what drives Planlagt. Think of a single schedule as a single thing to do somewhere in a regular interval. A schedule provides both the means on how to create tasks and how to consume them. Remember, this is the tight coupling we alluded to earlier that we really want. We will look at a bit of code later to explain this setup better. Wrapping all schedules is a synchronized cron task timekeeper. It is, at least for now, mandatory. It allows us to export metadata about task generation, which in turn gives us the tools to really introspect if we are not stalling our pipeline due to some undetected error. To the left, we have basically what we've talked in the first part about. It's a synchronized cron task, which implements a locking mechanism via Redis. This is what drives the task generation of a single schedule. With this locking mechanism, any running instance can temporarily assume the role of task creator, push task onto the message queue, and then reassign the role, or lock for that matter. We are not bound to a single instance, but instead can dynamically or automagically, as I like to call it, scale. Also, this synchronized cron tasks perfectly balance with our actual task consumption. The moment an instance gets the lock and starts to produce tasks, it automatically has less time for task consumption. Alas, we have a temporary workload shift where one instance focuses on producing and the other instances get to dedicate all their power to consumption. As soon as the task production, that means the synchronized cron task, has finished, that instance can too dedicate all its power to consumption again. You see, we really now reap the benefits of this architecture. But of course, Planlagt is only as good as the task you have in your system. If you only have one schedule which creates only one task at a time, you are not gaining anything in efficiency. Of course, you still get to eat your cake by having a lot more failure resilience, but you could have had that with a simple synchronized cron task, much simpler. So either by having a single schedule which produces a lot of tasks, or on the other end having a lot of single task schedules, or anything in between, you are using this architecture to its fullest. Just a thing to think about before you delve in it. Concluding the picture to the right, there is our distribution part. The producer is triggered via our synchronized cron task and pushes new tasks to a task manager. For now, Planlagt only ships a Redis-based task manager, but the interface is held open enough for other implementations in the future. I am actively working on a Kafka-based task manager, but it's not quite ready for prime time yet. As always, contributions welcome. Anyway, architectural-wise, you have this task manager, one per scheduler. If in the future you need to have different task managers, simply use different schedulers. Nothing prevents you from having multiple schedulers running in parallel. You just need to take a bit of extra care in configuration. But we will come back to this later when we look at some code. The main job of the task manager is, as its name suggests, managing tasks. This boils down to accepting new tasks via the synchronized cron task as talked about before, but also state transitions for tasks. Tasks can by definition have 4 states: ready to be processed, in processing, succeeded, and failed. All this is handled on the high level by the consumer and on the low level by the task manager. The task manager also provides a central point to pull tasks for processing by our consumers. For our Redis task manager, this means internally a message queue implementation, as we talked about before. One neat detail not directly obvious by this graphic is the fact that each running instance can have multiple consumers per schedule, if you wish to configure it this way. Go makes parallelization so easy, why not use it? So you can even parallelize your work if you start out with just one running instance. Some little detail I have left out of the picture for now is failure handling. Failure handling in Planlagt is twofold. For one, there is the failure handling inside the schedule. Tasks which fail to execute get put on retry and can be executed later again. This happens completely automatically and is backed by the task manager. The very same logic handles putting tasks in a failure state if they fail to execute one too many times. The exact number here are adjustable like anything else with Planlagt. Hidden behind each schedule, there's however yet another synchronized cron task running. It's called the cleanup task, not to be confused with the timekeeper cleanup task, which is something completely different. For now, this cleanup task has one job, and make no mistake, it's a very important one. Its job is to query the task manager for tasks which are hung in the processing state. So what does hung mean, you might ask? A task might become hung when the instance processing it crashes during processing and is unable to transition it back into a stable state. So this cleanup task looks for these hung tasks and transitions them into another state. Most certainly the task gets retried or put in the failure state. Now let's look at some code, shall we? Getting Planlagt up and running is pretty simple. First you need a task manager. And like I said before, for now there's only a Redis-based task manager, but it will suffice for our example here. With this, you can create a new scheduler. Cool, that was the easy part. But right now, the scheduler is not doing anything. We need to fill it with schedules. And this is where things get a bit more involved. Small implementation detail. The scheduler needs the Redis client for now, as it needs it for the underlying timekeeper to be created. In the future, this can hopefully be alleviated by making the timekeeper, or synchronized cron task for that matter, not exclusive to Redis. But this is a topic for another day. For now, let's just roll with it. So here is the code to create this schedule. Sorry for it being so small, but there really is quite some configuration to show. The addSchedule function takes a var arc of option style arguments, which allows you to customize nearly every aspect of the schedule. There are much more knobs to turn, and these are best to look up for yourself. For now, let's focus on what we have here. Firstly, we give the schedule a name. It's optional as all parameters, as the schedule ships with same defaults. But it's best to set one so you can differentiate schedules when querying the timekeeper for data. Next, we have the producer function. This function is called by our synchronized cron task as we configure it, and is expected to return one or multiple tasks. Returning no task is also valid if for any reason there's nothing to do. The producer config allows to customize the synchronized cron task which drives the producer. In its most simple form, we can give it a good cron expression. But we can customize much more. Look at the documentation of synchronized cron task for more. Completing the picture is the config about our consumer side. We define how many consumer workers each running instance should have, by default 1, and the actual function to handle or consume the tasks. So that's about it then. Let's do a small recap, shall we? We had some in-depth discussion about cronwork, what it is, and some examples therefore, especially what makes it different from a simple cron job. We talked about achieving this on a higher level, which then led me to introduce synchronized cron task as a viable solution. We had some in-depth architecture discussion on how to design a data pipeline and how we can make it really dynamic by using the pipeline not only for data processing, but including the very tasks into the pipeline as well. We really hammered home the problems we might encounter thereby and some solutions to these common problems. Concluding this talk, I introduced Planlagt, the framework which incorporates everything we have heard today. We did an in-depth analysis of each part of Planlagt, how it handles things, and how you can customize each and every knob of it. Where to go from here out then? Please, if you can, use my frameworks and give me feedback. Months of discussion, trial and error, and experimentation went into their development. They have seen a lot of personal usage, but they are ready to be used in the wild. There might be bugs, especially with Planlagt as it's the fresher of the two, but don't let that scare you away. If you like them, give them a star on GitHub, and if you're really awesome, please consider contributing to any or both of the frameworks and make them even more awesome. This leaves me now only with thanking you so much for your time. I really hope you enjoyed my talk and I was able to give you some inspiration on how to tackle cron work in your next project. We will have a final Q&A session now, where you can ask me anything that you're still burning to know. In case you don't get to ask a question, you can always drop me an email too, of course. Also, connect with me at Xing or LinkedIn if you want. Also, I'm always eager to receive feedback on my talk by any means you see fit. Liked or disliked anything, please let me know. Well, this is all then, I guess. This only leaves me with saying have a nice weekend and stay healthy.
Okay, welcome back everyone. We are ready to go live with Björn to answer any and all questions you have, those burning questions. We have 3 good ones already. Don't be shy. Okay, 4 questions now. Great. Let's bring on Björn for these questions here.
Hi.
Hi, welcome back. Thank you so much for that talk. And first of all, I just want to say again, even if it's virtually this year, we're very happy to have you at GoLab.
Thanks for having me.
Absolutely. Did you have anything you wanted to say about GoLab in general or your participation?
Nothing so far. Just a small sorry. If you tried to find Planlagt on GitHub, it may have turned up an empty repository so far. Because of matter of fact, I broke my arm and was unable to finish the library on time for the talk. But rest assured, the library will come. I am actively developing it, and it should be a matter of a few days. And again, sorry about that, but life happens.
Yeah. Please have some patience for pure Björn for that. Yeah, life happens, definitely. So let's go ahead and get on to the questions. We've got 4 so far, all by Ilan.
Right.
He said that he did something similar, and so he has some good questions. First question is, how do you handle stale locks if a lock is orphaned?
I handle it good, I suppose. To be serious, synchronized cron task itself basically doesn't handle it. It has a detection for it, but it doesn't do anything in particular with it. What I said in the talk, the blocks are intentionally specified to be very short. So I think the default is, a second or 2, and instead synchronized cron task refreshes the lock while the task is still running. So if the service crashes, the time to detect if the lock is stale is pretty short. But other than that, like I said, synchronized cron task does not have any means to do anything with that. On the other hand, Planlagt actually has. So if a task, that was actually wrong. Well, Planlagt does not have any particular means of handling stale locks. Actually, like I said, it has a retry mechanism to handle tasks with fail, but nothing in particular about locks. So I hope that answers the question.
Sure, thank you for that. All right, moving on to the second question here. How do you handle the problem of a source the job is polling not handling your requests as you are polling too fast? Is it retry, circuit breaker, or back off?
Yeah, like I said, it is retry logic. Like I said, synchronized cron task basically is pretty dumb in that regard. It doesn't have any particular failure handling. But Planlagt has actually two things that you can use to handle this scenario. One, in case for failure handling. So each task itself, for one, has a deadline. So if it's not processed in time, the task itself is discarded. And for the for failure handling, so if exactly that scenario, if you execute a task and it fails, there is a retry counter, how often it is to be retried, and it has a back-off mechanism, so it doesn't endlessly retry, but there is some time it waits. Yes.
Okay, thank you. All right, moving on to number 3. Have you considered creating an external DSL for defined schedules tasks that could be just discovered in a specified folder?
I have not considered it so far, because at least the way I used Planlagt so far was very code specific. So it was very specific to the things to the task itself. But there was very specific code. I don't know how I would go to abstract that and put that in a DSL. So I have not considered it so far, but I might give it some food for thought in the next few days.
Sure, sure. It's always good to bounce ideas off each other as well.
Right.
All right, our last question here. Do you have a facility to maintain dependencies between tasks?
I do not. This is actually something I have. I haven't considered it, but actually for the personal project that is using Planlagt, I did encounter that problem. Like I said, the birth of Planlagt came from the fact that I needed to pull a lot of APIs, and of course, in the end, I have to reassemble this. But the way I did it, it was handled by some application logic down the stream. So basically, my Planlagt tasks pull data and put it on the Kafka topic, and services down the stream assemble the data when it comes in. So there is no logic in Planlagt or synchronized cron task, for that matter, to handle any dependencies between tasks apart from failure handling. So this is a very, very interesting thought.
Yeah, another good one to keep in mind. All right. Well, I think that was our last question for today. So before I say goodbye and do all the goodbyes, I want to first of all say this was the last talk of GoLab 2020. But I really hope that everyone can stick around. We do have the closing ceremony happening at 7 p.m. So please stick around if you're just getting out the door. We have a special surprise for you. All right. So I want to, first of all, again, thank you, Björn, for your contribution. And hopefully, whether it be virtually or in person, we definitely hope to have you in the future editions of GoLab.
I'll try my very best and try to finish the frameworks for next year before the talk. So.
Don't worry. And I hope your hand heals fine, too.
I hope so, too. So.
Yeah. Things always happen at the last moment like that.
Indeed.
Yeah.
Literally.
All right. Yep. All right. Well, we'll see you around and take care. Hope you enjoy the rest of your evening. Thank you. All right. Goodbye. And thank you all for joining us. And if you liked it, of course, he asks for feedback. We also would love to do that, love for you to do that on the agenda page. And so, like I said, we hope to see you all at the closing conference happening at 7 p.m. So 12 minutes from now, given to us by Matteo Benci of GoLab and Develer. We have a special surprise to thank you all for coming this year. All right, hope to see you there. Goodbye.